addresses for our electrons today. These addresses are given a fancy chemistry name. The address of our electrons is called electron configuration. And that's what we're going to learn how to do today. We're going to learn how to write the addresses of where our electrons are inside of the atom. Tell us what energy level they're in, what sublevel they're in, and then finally, what orbital are they in, and how many electrons do you have living together in the same orbital or sublevel. Okay, that's our goal for today's lesson. And so with my pencil, let's go ahead and write down the word electron configuration. That's our main topic for today. Make myself a note. Electron configuration is the address for where electrons, air quotes, live inside the atom. Just like real addresses, there's a format for writing electron configurations. There's a proper grammar for writing electron configurations, so we're going to discuss that. The format for electron configuration. I think it's best to just show you an example and then explain. Let's say it says 4p or exponent 3. Let's say some electrons have this address of 4p3. Well, what does this mean? The coefficients in front of the letter, that big number, this 4 right here, and I'm going to highlight this. That number 4 tells us what energy level the electron lives in. Okay, so I'm going to write that down. So that coefficient is the energy level. And I'm all about colors. And so I'm going to say, okay, that coefficient was that big number 4. That tells me the energy level. That'd be like you telling me you live in Virginia Beach. So same thing here. We're dealing with electrons located in the 4th energy level. Hey, but remember, we can get more specific than that. We can take it a step further. Just like with your physical address, you can tell me what neighborhood you live in, right? Same thing here with electrons. I can be a little bit more specific, and that's where the letter comes into play. The letter, for this case, it's P. That P represents the sub level, equals the letter. Okay, so now I know more about these electrons. They're inside the P sublevel, which is located inside the 4th energy level. And then I have an exponent. And for the sake of my notes, I'm going to go ahead and circle that. That exponent that I've circled equals the number of electrons that live inside of that sublevel, located inside of that energy level. So if I read this as 4p3, we would say, I know that there are 3 electrons living inside of the p sublevel, which is located in the 4th energy level. Okay, so there are 3 electrons inside of the 4p sublevel. Another vocabulary word, valence electron. Valence electron is an electron located in the highest energy level. AKA, they are the farthest from the nucleus. And so that's a new vocab word for me. Valence electron. I'm going to go and grab my highlighter. Valence electron. All right. So you're like, okay, great, Miss Wong. You are speaking a foreign language. I have no idea what you're talking about. I don't know what we just drew here. I don't know what's going on. Let's take a look at some examples. Okay, and I promise it will start to make more sense. Let's take a look at some electron configuration examples. Number 1. Let's say I give you this address, 1s2, 2s2. We're going to do a few things with this address. The first question we're going to answer, what is the highest occupied energy level? I know that there are 7 energy levels inside a given atom, but they don't all have electrons every single time. The principle is that we always put electrons inside the atom closest to the nucleus first. We fill in the first energy level, then we fill in the second energy level, then we fill the third and work our way out. So not every single energy level is going to contain electrons. So this question is asking you, of the energy levels that have electrons, what's the highest number? Which one is farthest from the nucleus? Okay, so I have to remember the format of our electron configurations. The coefficient represents the energy level. So I'm going to continue with my highlighting pattern. In my notes, I had highlighted the coefficient with blue. So I'm just going to look at the coefficients. That's all I'm looking at right now to answer this question. I have a coefficient of 1 and I have a coefficient of 2. I'm going to highlight the biggest coefficient present. Our highest energy level. The biggest coefficient that we have is 2. So the energy level farthest from the nucleus that contains electrons is the second energy level. All right, cool. Question B. number of valence electrons. Yeah, Aiden, that's right. 2. Because I'm looking here. The highest occupied energy level is level 2. And look at how many electrons we have inside of that second energy level. Aiden, notice that, hey, right here, that represents your valence electrons. We have 2 electrons inside. Okay, so the number of valence electrons is 2. There's 2 electrons inside of that second energy level. Next question. What is the total number of electrons inside of this atom? The total, not just the valence, but everything together. To do this, you're going to add all exponents together. Add them all up, because I know that the exponents represent the number of electrons. So I'm going to add 2 plus 2, 2 plus 2. So that means there are 4 electrons total inside of this atom. Next question, letter D. Assuming that this is a neutral atom, meaning that the number of electrons equals the number of protons, what element is this? You look at your total number of electrons. Assuming we have a neutral atom, if there are 4 electrons, then there must be 4 protons as well. And so I go and grab my periodic table. Very helpful resource in this class. You use it every day. I'm looking for number 4 on the periodic table. Anyone find it? Yeah, Tommy, Be, beryllium, capital B, lowercase e. And it's very important that we're writing the symbol exactly as we see it on that periodic table. The first letter of element symbols are always capital. The second letter is always lowercase. Okay, all right. Let's try another one. Example number 2. We'll go through the same thing. 1s2, 2s2, 2p6, 3s2, and 3p2. Okay, I'll give you a moment to record that. Okay, we're going to go through the same set of 4 questions for this example. A, what is the highest occupied energy level? And so for energy level, I think one thing, coefficients. That's what I'm looking at. I need to find the biggest coefficient. So I got 1, 2, 2, 3, 3. Okay, 3 appears to be the biggest coefficient. So I'm going to highlight the 3s. Those are highest occupied energy levels. So my answer is 3, because that's the largest coefficient present. Question B, number of valence electrons. Remember, valence electrons are those electrons in the highest occupied energy level. So I have highlighted here that energy level number 3 is the highest. I have 2 electrons inside of 3s, and I have 2 electrons inside of the 3p. Because all those electrons reside in the 3rd energy level, which happens to be the highest occupied. They are all considered valence electrons. So for this one, because I have the number 3 twice, okay, I have to add those exponents together. So it's going to be 2 plus 2. I'm going to get 4 valence electrons. Question C, total number of electrons. All the electrons in the atom, valence and the other ones. So that means I add all the exponents together. So I'll just start here from the beginning. We're going to add 2 plus 2 plus 6 plus 2 and then plus 2. Okay, so 2 plus 2 plus 6 plus 2 plus 2 equals our total number of electrons. And I get 14 electrons total. Question D. Assuming that this is a neutral atom, meaning that the protons will be the same as the electrons, what element is this? So again, I go and look at my periodic table. I'm looking for number 14. Anyone find it? Excellent. Yes, good. Silicon. Capital S, lowercase I. Si. All right, example number 3. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Ooh. And again, I'm going to ask you the same 4 questions. Okay, so I want you to try this one on your own. We'll do the same process. Given this electron configuration, this address, if you would say. Okay, thank you for your responses. So check your answers here. The highest occupied energy level means we're looking for the biggest coefficient. The biggest number coefficient is the number 4. And so that would be the 4th energy level is the highest one, farthest from the nucleus that contains electrons. Letter B, the number of valence electrons. Again, that comes from the highest occupied energy level. So I have 2 here and I have 5 there. So I have to add those numbers together. So 2 plus 5, this has 7 valence electrons. The total number of electrons comes from adding all of those exponents together. So I have to add 2 plus 6. Oh, sorry, that's 2. 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 5. And that's going to give me an answer of 35, right? What do you guys got? Yes, 35 total electrons. Then based off of that, assuming that this is neutral, this is going to be Br, bromine. So very good for those of you who were able to determine that this was bromine based off of its electron configuration. So that's the format of electron configuration. That's one of your learning targets for today. Can you look at this electron configuration and answer these 4 questions? Another part of today's lesson is, can you do the reverse? Meaning, if I told you you got an atom of bromine, can you write this electron configuration? 1s2, 2s2, 2p6, 3s2, etc. Okay, that's the second half of our learning objectives for today. And so I'm going to show you how to do that. Okay. It looks scary, right? It looks like craziness. Trust me, it's not as bad as it looks. Example number 4. We are going to write the electron configuration for S. That's sulfur. I'm going to write the electron configuration for sulfur. Okay. Maybe it's just best to watch and listen to me explain. Okay, just hear me out. All right, I'm going to show you how to do this. Just watch. Don't try to write down anything right now. I just want you to just watch the process. So remember this thing that we drew at the beginning of notes? We've broken up our periodic table into 4 main sections: S, P, D, and F. You read yesterday that the rows equal the energy level. The periodic table is going to help us write these electron configurations. And we're always going to start reading that periodic table where hydrogen is located, where we wrote the word start earlier. Okay, number 1, we start with element number 1. And so if I'm looking at a real periodic table, I know that I labeled these 2 as S, this one as S as well. And I labeled this section D, and I labeled those 6 as P. Hear me out. Here we go. If we are starting here, what row are we on? We're on row 1, right? Row 1. Well, rows mean energy levels. And in electron configuration, coefficients mean energy levels. So we're right now going to write a 1 because we're starting on row 1, coefficient 1. And what does my periodic table tell me? Row 1, where hydrogen is located, it's in the S section. So I'm going to write a lowercase s. Okay, that's where I'm at. That's where I start. And then the next part, we're going to start filling in electrons. Well, that one s orbital can hold up to 2 electrons. And so I'm going to read this like a book, left to right, and then down the page. So if I'm starting here where hydrogen is, okay, check. I'm going to move over on the same first row to where helium is. Well, I'm highlighting in blue right now. Helium is also row 1, and I've labeled it as S. So that means the second electron is also in 1s. Where's the third electron going to be? The third electron is right here, number 3, where lithium is located on that periodic table. I've now highlighted in yellow. Well, isn't that in row number 2? Good, yeah. And what area of that periodic table are we in? We're in the S block. I keep going, keep reading that periodic table. The next element is BE, number 4. Well, where is BE? It's in row 2, section S. Okay, so it's that fourth electron is also in 2s. Keep going, keep reading the periodic table left to right. The 5th electron, where boron is located, still in row 2, right? But now, where is it? No longer in S, is it? It's now in the P block of our periodic table. And so I'm going to continue reading this periodic table in that fashion. Okay, so I go on to carbon. It's also in 2p. I go to nitrogen section. That's also in 2p. Oxygen's in 2p. Fluorine is in 2p. And neon is in 2p. Then I keep going, right? Next layer, I'll do a different color. Now where sodium is located, that's in row 3. And look, we're back in the S section of our periodic table. Magnesium is going to be 3s. Aluminum's location, though, isn't that going to be 3p? 3p. And I keep on going until I reach sulfur. So I know that this was 1s, and that was 2p. So for the electron configuration for sulfur, we have to state how many electrons we put into 1s. We put 2. I put an exponent of 2. Then I state the next section to be filled was the 2s section. And how many electrons can fit inside of 2s? 2. I put an exponent of 2. Where did we go after 2s was filled? We went right here. We went to 2p. And count. How many electrons did we put into 2p? 1, 2, 3, 4, 5, 6, right? Oh, corresponds to those 6 columns that we drew. So I'm going to put an exponent of 6. And then after that, we went to the third row. 3, and it had a letter of S. I count. How many boxes, how many electrons are in that 3s section? 2. After 3s, where did we go? We traveled across. We went to 3p. And count with me now. How many electrons did we put inside of 3p? We put 1, 2, 3, 4. Stop. Because we've landed at sulfur, the element in our question. So I'm going to write an exponent of 4. So that's my electron configuration for sulfur. 1s2, 2s2, 2p6, 3s2, 3p4. I'm telling you how many electrons are in each sublevel inside of a sulfur atom. Okay, so that's what we're going to write down. And to our notes, for the answer, we're going to write the answer is 1s2, 2s2, 2p6, 3s2, 3p4. So ask yourself, is that right? What's one way we can check our answer? Remember the thing about the exponents. If you add all those exponents, it tells you the total number of electrons. If I added all of these, I should get the atomic number for sulfur. So 2 plus 2 is 4, 16, 10. I get 16 for the total, and that matches the atomic number for sulfur. Okay. I know that was crazy. Let's try another one. Let's write the E configuration, and I'm going to abbreviate now, E config for, let's go, Na, that's sodium, and sodium is number, make a cheat, number 11 on the periodic table, number 11. Okay. So we're going to go through the same process. You start with number 1, hydrogen. It's in row 1. So that means that puts us here. We'll delete what I have. We'll go through the same process for sodium. All right, so we'll start there where hydrogen is. That's 1s. I move over to where helium is. That is also S. After that, we go to lithium. We go to beryllium. Then we go to boron, carbon, all of these guys here through neon. Okay, so right now we have 1s2. After that, we went to the second row. That means it's 2, and we're in the S region, so that is 2s. I can fit up to 2 electrons for S because there's 2 columns in S. And then I travel across. I'm still on the second row, but now I'm entering the P block of our periodic table. So it's 2p. And if you count how many columns you drew for 2p, and we filled in all of them, that is 6. And then I keep on going until I reach the desired element that I'm solving for. Here's sodium, number 11. It would be 3, and we're in the S region, and we stop there, 1 electron gets filled. Okay, so that's my answer for sodium. 1s2, 2s2, 2p6, 3s1. Write that down. 1s2, 2s2, 2p6, 3s1. All right, we've got time for a couple more. All right, let's write the electron configuration for germanium, Ge. Number, help you guys out, 32. So in writing the electron configuration for that element, we always start with number 1, where hydrogen is. So the rule is we had to start with the first energy level. When we fill in electrons, we always start with the first energy level, and then we work our way farther and farther away from that nucleus. So back to that periodic table. Germanium is number 32. So we're going to have to fill in all of these that I'm highlighting in blue here. All of these until we get to germanium, number 32 on our periodic table. All right, so follow with me. We got to start with number 1. 1s, and I count 1, 2 electrons can fit. The first row is full. Now I move to the second row. So I put a coefficient of 2. We're in the S region, so I write an S. And then I put in 2 electrons, so I put an exponent of 2. I travel across. I'm still in the second row. But remember these last 6 columns, that's the P block of our periodic table. So we're going to write 2P and count 1, 2, 3, 4, 5. We can fit 6 electrons in that P block. After that is full, we go to the third row. And we're in 3s. And I can fit in 2 electrons. So I'm going to write 3s2. After 3s2 is filled, I travel across. We're now at 3p. So I'm going to write 3p, and I count how many electrons can fit inside of 3p. And I count 1, 2, 3, 4, 5, 6. All right, 3p's done. Now we're going to go to the fourth row. And so I write a 4. And notice that we're back at S. Okay, all the rows start with S. I'm going to write 4s. And I count how many boxes are in 4s. 2. Now where do I go? After 4s, I got to keep on reading my periodic table on the same row. Now we enter the D block right here. I'm circling. D block. Starting with number 21, scandium. So the letter is going to be D. But remember when we drew our makeshift periodic table today? I had you write something in that D region. Let me refresh your memory. There it is. Note what I had you write in that D block. In the top left-hand corner, I wrote 3D. This is something very tricky about Ds. The energy level of D is always 1 lower than the energy level of S from the same row. So that means on a given row, the coefficient of D is always 1 less than the coefficient of the S. So when I get here to scandium on the periodic table, it's going to be 3D. Just watch out for that. I'm going to write 3D. You don't have to put a circle around, but I'm circling it for emphasis. That's 3D, guys. Because the rule is the coefficient of D has to be one number lower than the coefficient of S that came before it. And so since we're on 4S, then that means it's going to be 3D, one less. And now count with me. How many boxes are in that 3D section of the periodic table? And so you're going to have to look at a real periodic table, or you can look at the one here on my screen. We're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After that 10th one, now I'm back into the P region. So in total, we were allowed to put in 10 electrons into the 3D section. So the exponent is 10. Well, where do we go from here? We're not done yet. I got to keep on reading that periodic table. Now we enter the P block of the periodic table. Now we're back to 4. Okay, so P and S are always going to have the same number. It's just D is weird. So 4P, and how many electrons can fit into 4P? Count with me. 1, 2, 1, 2. What's the other language? Gosh, I'm blanking. German. Eins? Anyone take German? No, is that not right? Eins? Yeah? I'm totally butchering it. Eins? 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 1, 2. Oh no. On the.
It's eins, zwei.
Oh, eins, 5. Okay, thank you. But this is going to be an exponent of 2. There you have it. You have the electron configuration for germanium, guys. Please make sure you have this written down as your answer for germanium in your notes. And so now you can just be, okay, anyone ask me for the electron configuration of germanium? I just need my periodic table and I can spit this out, 1s2, 2s2, etc. Okay. But it's going to take some practice. So for practice, you have an exit ticket waiting for you inside of Schoology. You can attempt up to 3 times today. But you need to self-evaluate where you're at. Okay? I know this was a long lesson, and I appreciate your patience, and I appreciate your participation. And I know that stuff looks crazy. It is like crazy chemistry lingo for us chemists. But all it is, it's called electron configuration, and all it is, it's an address for our electrons. We're telling someone where the electrons are located within that atom. Okay. And Madison, to answer your question, when you get to row 5, Madison's asking me about row 5, it would be 5s, and then when you get to the D block, it would be 4D. Very good question, Madison. So when you're on row 5, it's 5s, 4D, 5P. Okay. All right. So exit ticket for today, due by tonight. You can try up to 3 times. And I will see you guys tomorrow. I get to forewarn you.